Thank you, Jim. Hello, can you hear me now? Perfect. Thank you, everybody. Today, I just want to share a little bit of the work that we are doing here at SIGA in terms of evidence aggregation. And I want to start with the question on why should we care about evidence aggregation in the first place? And I would argue that a very important reason is that the evidence that social scientists produce could be used more effectively in research and policy if it wasn't isolated in individual papers. The problem is that there is only so much you can learn from a single paper in a specific context, but also learning from many papers is very expensive and requires a lot of effort. For example, there has been a proliferation of RCTs, randomized controlled trials, in economics and across many areas, in particular international development, where RCTs are used to estimate the impact of a social program or the effect of a specific intervention. And even then, it's really hard to know what actually really works. And there has been some meta-analysis done for specific interventions, but learning what actually works in terms of the social programs or the interventions that are being studied requires building an evidence base that is robust and complete, and that's very expensive. How much? Let me put a number on that. So we estimate that there is anywhere between 7,000 to 10,000 RCTs published in economics and related fields. For example, the development portal by 3IE, which is a really fantastic tool, includes metadata for over 8,500 RCTs. That includes published and non-published RCTs. And at SIGA, we have collaborated with other organizations in the last few years trying to build this evidence base using human encoders. So, for example, we work with the World Bank in the IDEAL project, and we are collaborating with Evidence, which is a project led by Dean Carlin at Northwestern. Perhaps the most significant output of this collaboration is the IDEAL schema, or the schema that we use, which we believe is the set of fields that fully represent a randomized controlled trial in terms of data. And this schema has been applied to specific collections, for example, cash transfers, early education, interventions, or, for example, the Evidence currently is conducting a meta-analysis on graduation program, which is a type of intervention. The problem is that this is very expensive and very slow. So based on some numbers that we get from these projects, encoding an entire paper could take up to 20 hours for a single paper. It could cost $1,000, and this may vary depending on the complexity of the paper, and also the process to, like, for quality assurance and to guarantee that you are managing a group of students that are doing this in an effective way. It's also very expensive. And I would say that the status of these projects, at least what we know, is that there have been at least, or roughly 500 studies that have been encoded so far. It's really difficult to know because there is some overlap between those studies. But as you can see, we are not 10% all the way if we want to build this big evidence and robust evidence base. Now, during this process, we consulted with a lot of experts. Many of them were LLM experts, and they were very surprised we were doing this with humans. They were very eager to point out that human error is also present when you collect data, so building a ground truth based on just human encoding could also include some errors. And also, they realized that this is very expensive we do it with humans. So they always suggested, why don't you use AI? But what does that mean exactly? So they mean use large language models, LLMs, to track metadata from papers. And there are many flavors to do this. You can try different ways. For example, you can go to ChatGPT, upload a paper, and start asking questions. That, of course, is really impractical to do it at scale, but you can try it. It's, I think, for most part, free. Although I should say that you may be evaluating the terms of service of the publisher, which I'll touch in later. But there are millions of students doing it anyway. You can also do some very sophisticated architecture, which include like agentic orchestration, which involves having agents determine their entire workflow from extraction to validation and the resulting output. We have been quoted around $50 per paper, which is much less than 1,000. The problem is that using LLMs involves and comes with some risks. I'm just going to mention some some of the ones that I think are more important. The first one is hallucinations, and I guess you know what this is. When you go to ChatGPT, you ask a question, sometimes it invents or hallucinates the response. And if you want to build a ground truth data, or not a ground truth data, if you want to extract information that was meaningful and useful for policymakers and researchers, you want a level of precision that perhaps an LLM might not bring by itself. There is another problem called context decay, is that the amount of information that you can send LLM for processing is limited, and the more you use of that context window, as it's called, the worse the performance it gets. And this is important because every time we send a paper to the LLM, where if you're including instructions and other details, for example, a configuration for the model to behave in a way that you want it to behave, you are pretty much sending an entire book worth of text, which involves a large context window. And more importantly, perhaps for the conference today, is that once you rely on LLMs to do this kind of work, you are outsourcing a lot of the decisions regarding the workflow and distraction process to the LLM. And although I'm very optimistic of the use of LLMs for this kind of work, it makes me deeply uncomfortable to relinquish control about what is being produced. So I want you to keep that in mind. So when we consulted with experts, we also asked them, why don't you try it? And this is not hard data. This is mostly speculation, not a speculation, but it's anecdotal evidence, because they provided some tests. It was not very scientific, I would say, but this is also my experience as well. And the main takeaway here is that there are some fields for which the LLM is going to do a really good job, like a study level information and classification problems regarding the location of an experiment, for example, or what is the unit of randomization. You can pretty much guarantee 100% accuracy. And that kind of makes sense, because when a paper presents the location of a study, for example, the country, that only may appear once, and there's little ambiguity about that aspect. And even if a paper mentions multiple countries, you can specify a set of instructions that parse that edge case out of the data. There are other types of fields, which I call relational metadata, in which the LLM has to do a lot more inference. So they need to learn something first in order to apply something later, in order to do some extraction. For example, outcomes. So the paper needs to define what the outcomes are for the LLM to find it, or the empirical model. The LLM needs to understand what the model is in order to find the letter in the data. The problem, although for those fields, we see that there is a lot more spread, but the LLM can do a good job. And this will vary depending on the content of the paper, but also the set of instructions. What is not good is that for the information that we care about, which is the treatment effect level data, for example, the point estimate or the precision level, LLMs cannot do it very well. You might do it for a subset of papers with 90% accuracy, but at scale, it's really hard for the LLM to do it. We don't know really why this is the case, but we just speculate that the task is just too complex and too specific for the LLM to do it right. So the question is, can we solve this problem? So we are trying, and we're basically, our approach is based basically in 3 steps. The first one is to move away from an analytic definition of what a treatment effect is. For example, this is the formula that economists will use to understand a treatment effect, the average treatment effect of a program, which is the difference between a treatment and control for a given outcome. The problem is that this encodes a lot of information that doesn't map to what the paper is presenting. So what we do is to move away from that and use an information-based definition of what a treatment effect is, which for us is a combination of certain dimensions or factors. In this case, we're using contrast, which is like, the treatment and control as represented in the paper as labels. We have the outcome, the unit, the period or a round of observation or estimation, and the specification, which refers to the empirical model that we use. And this is important because this is the framing that we use in the prompts to instruct the LLM to extract the data. We instruct them to look for what is being measured or what is the intervention that we care about, on the effect on who or whom, when that effect was measured, and how, essentially. And as I said, this is important because the prompt that you provide to the LLM are very different. For example, if you are thinking about this, you may say, extract the treatment effect, which is assuming that the LLM understands what treatment effect is, and you are relying on what the LLM learned during training about the semantic representation of those words, which is very different to ask, extract the value associated with a unique combination of factors, which is this. For example, what is the impact of cash transfers on the control group, on the income, annual income of a family, at headline using, I don't know, OLS or something like that. It's a very different ask. The second thing we do is to have a blended approach, which I hope is more disciplined in the sense that we are not outsourcing the treatment effect extraction to the LLM. We are using the smaller non-reasoning models for two reasons. One is that it is faster and cheaper. So we are using ChatGPT 401. Before we were using 4.0 mini. And the second reason is that these models allow for certain configuration that make the output more deterministic. So for example, if you use non-reasoning models, you can define a temperature parameter, which is just a sampling parameter, but the LLM crowd tends to describe it as a creativity parameter. So you are allowing the LLM to be more creative. We also use a fixed seed, so in order we can reproduce this process every time we run it. In addition to this, we have developed a linearization algorithm, which I will explain in a second. And this is what is actually determining what treatment effects are being extracted. And this is here. In a summary, it's just reducing the dimensionality of tables, which is the data environment where the treatment effects are reported. And that will also give us some way of verification of the treatment effects extracted by the LLM. I just want to point out that we do a lot of processing of the papers. We don't just send PDFs, because a lot of the variability that we get in the output actually comes from how the data is parsed. So we are working with the UC librarians to get access to the papers as the structured data using an XML format. And this facilitates a lot of the work that we do, and actually is fundamental for the table linearization algorithm that we use. We also work with PDFs, it's just that it's a lot harder. But the space is moving so fast that 3 months ago, I would say that there is no open source tool that will get you the correct layout for a paper using PDFs. But now we found one that is pretty good, which is called MyNearU. And maybe in another 6 months, this is a problem that has already been solved. For now, we are mostly working with XMLs because we have access to the data from the publisher, and also because we want to be mindful of copyright issues that may prevent us to publish the data later. I just want to mention the linearization process is that these are 4 ways in which you can see the data in a way. So for example, this is the original paper, table 1 from the paper. And the layout is very important for humans to understand the information that is built in this table, for example. But this is not what the LLM sees. What the LLM gets is a version of this, which is a string of text that may not or may not capture the perfect layout or the layout in which the author tried to represent his data. And depending on the model, the parsing of the PDF might be not just trying to extract the table from the paper, but it may send that information as a picture, and that picture may get transformed to pixels, and from pixels to text. And in the entire process, some information may get lost. So instead of that, we transform the tables using our processing into HTML. And my assumption here is that since LLMs are trained essentially on the entirety of the internet, they are pretty good at reading HTML formats. And in this case, we can refer to parts of the table not as concepts, for example, columns and rows, but as a specific tags depending on the HTML formatting. So once we have the HTML version of the tables, we essentially reduce the dimensionality and transform, which seems like just columns and rows, but actually encode a lot of dimensions. For example, in this case, there are outcomes here, there are statistical measures in the columns, there are different periods. But what we do is essentially transform that into text, but it's formatted in a way that the machine can actually read in the way we want it to read it. So how this works, essentially, we have the table. let's say the LLM correctly identified that emotional support is an outcome. So we can tell the LLM that he needs to look information for this row, but there is a lot of numbers that might be extracted, right? But we also get information from the period or the round of data collection. So if the LLM correctly identified post-kindergarten as a period, we can filter all these rows or all this information and focus on this. And on top of that, we can get the specification, which is a little bit trickier in this case because it's not present in the table, and narrow everything down and filter all the additional information to get the number that we care about. If we don't do this, the LLM might do, I think, 3 potential extractions. One is it may extract this number, 4.810, just because the label of this camel includes the intervention label, which is UCP. It may extract the correct number, which is the difference, or may extract this additional column, which includes the effect size, which is technically correct, but it's not the number that we want, because we don't know how that effect size was calculated. The tricky part here is that the specification is not technically in the table, it's in the captions or even the title of the table. And that makes this process a little bit harder. So the linearization process is the weakest part of the pipeline, essentially because it depends on the layout of the table. And we wanted to make it work for every table in every single paper. Here, I just wanted to show you some results, but I want you to take it with a grain of salt because this is not enough testing. We have a sample of almost 8,000 estimates extracted from 341 tables from 74 published articles. And I say that take this with a grain of salt because this is not a representative sample of anything. We are mostly using XML, which helps a lot, but also we are including papers that have tables that are particularly bad, horrible things. So I've done the coding manually myself, and there are some tables for which I cannot understand what the treatment effect is. So I wouldn't expect the LLM to do it anyway. So it's like we need more testing, that's what I'm trying to say. And I'm comparing different modes of extraction. So the first one is the LLM alone. We're asking ChatGPT 4.1 to extract all fields using the schema, the HTML tables, which helps, and the text from the paper in a smart way. So we chunk the text, and we only send the information that is relevant for a specific field. So if the LLM is extracting the empirical specification, we only send that information to the LLM. So we then combine the LLM with the linearization algorithm, which helps. And here I don't want you to focus on the magnitude. I want you to focus on the differences between these two, again, because this is not representative. But the LLM alone will do like 60% content quality. Oh, let me just explain that. We have 2 measures. One is coverage, which is a measure of the quality of the extraction. And the other is accuracy, which is actually measuring whether the LLM was accurate in extracting the right cell in the table. In terms of, this is a measure that I use in machine learning, is the F-score, and they say that around above 80% is a good measure, and here we get 70% for the LLM alone. When we do linearization plus the LLM, we get a better result except for content quality. And this kind of makes sense because in this case, we are extracting more fields per table, so there are more opportunities for the LLM to get it wrong. And since this is the processing is sequential, these errors propagate downstream. The biggest jump or improvement in content quality and accuracy is actually validation. So when I echo the point made in the previous presentation that there is an argument to have humans in the loop doing this job with LLMs, because otherwise it's really difficult to extract this information properly. And now, finally, if we combine validation and the linearization algorithm, we can guarantee that we extract all the treatment effects that we care about. Of course, this is like over-engineered because we use those 74 papers to develop the linearization algorithm and to extract the data that we care for that algorithm itself. So we will need to test out of sample how this behaves. Yep. And I just want to go back to the framework that we established at the beginning, because with this framework, we can start asking some very simple questions. So for example, my expectation is that for simpler designs, the classical treatment and control kind of experiment, the LLM is going to do relatively well. And it kind of makes sense given this framework. If you have this treatment effect defined in this way, there are simply fewer things that the LLM needs to extract. And this is orders of magnitude fewer things, because the contrast essentially disappears. There is only one treatment and one control. But surprisingly, it does worse. For simple design, the LLM gets it even worse. And more importantly, this is a case in which the linearization algorithm is not going to help. Again, we need to investigate more about what's going on. But let me just go back to this example in this table and going back to the specification not being present in the table. So while it is true that if there are simpler design, there are fewer things to look for in the paper, there is also less information that the LLM can use to actually get the right number. So what I've noticed, especially after verifying the data, and what I mean by human verification is just Joe and me verifying the data. What we see is essentially that in simpler designs, authors are less likely to label the treatment arm in the tables, like in this case. So it's really hard for the LLM to actually get the right number because it's nowhere there, it's in the caption. So you need to do some pre-processing in order to teach the LLM in context learning what it needs to look for. So these are interesting results. Again, all these results are significant, and the only way to solve the problem is actually with validation. So another argument to bring humans in the loop and try to make this process more robust. So as some next steps, there's like a number of technical improvements that we can make. We are working with professors of computer science at Northwestern University and students as well to make this process more robust. We want to make this a public access tool and also publish the data. But this requires making the process a little bit more robust. And in particular, we want to bring humans in the loop, not only to create ground truth data that will be used for validation, but also as a training exercise to bring researchers from lower and middle income countries to be part of the project. And in terms of research, as I said, we want to publish the data and make it accessible for meta-analysis. And there is also a class of estimation and prediction problems that use aggregate RCT information as a benchmark, that will benefit from this data. We also want to know why this works or why it doesn't. And specifically, there is an important question about, are some papers better than others? Not in terms of content, but in the way that they encode information. So for example, you may hypothesize that for some disciplines where there are standards and reporting protocols, the LLM might do a better job because that data should be presented in a standardized way, which you can use and instruct the LLM to extract it, versus a field like economics, which is just slowly catching up to this, but is not really prevalent in all papers. And that's all. Thank you.
Thanks a lot for the talk. It was super interesting. So I really like the structured approach you have, and you gave very good reason why you use GPT 4.1, because it's less costly. Mm-hmm. I'm wondering if you could just plug in a more modern version, like 5.2, and then do a cost-benefit analysis of like, okay, we can use a more modern tool, it will do better, but it will cost you a lot more, and then people can decide for themselves which method they want to plug in.
Yeah, for example, that's the kind of testing that you should do in order to say the LLM does well or not. You need to try several models. We actually use 4.0 mini and 4.01 for testing. Moving from 4.01 mini to 4.01 is a massive improvement, but it gets marginally lower over time. The other problem with flagship models like GPT-5, for example, is that all of them are reasoning models. And as I said, the moment you bring a reasoning model into the mix, you lose a lot of control about what is happening in the background, which I think is important to have in mind. And the other reason is actually I will go the other way. I will try smaller and smaller models, because if we want to make this a public good, we want other people to try it. So there are open weight models that are getting better and better over time. So we'll actually would like to go that way instead of giving OpenAI more money. There's a question at the back.
Hi, Mario from Stanford University. As you mentioned, in biomedicine, a lot of RCTs are a little bit more structured, but you have now two really excellent tools. One is called AutoSR and the other one is called RRI, which are exclusively built to extract data from RCTs and have accuracies bigger than 96 to 99%. I would highly advise to test them because they cost around 15 to 25 cents per paper, and they give you quite a lot of variables. So what we do a step beyond that is not limit yourself to the differences, but also extract the N and the effect size and everything else, because when you extract everything related to it, it reduces the possibility that the wrong number is extracted, or you can see if the same number is extracted twice, that something in the paper might be, not ideal paper in the way it was reported.
Yeah.
But these tools right now are being tested because they've been trained on systematic reviews that already extracted data from RCTs. You have a golden standard database on which these models are trained. So they are not using predominantly NLLs that are not trained for this, but they are models now trained exclusively for data extraction from papers. And they provide you reasoning. So if you use PDF, they highlight the text where the number was extracted and give you a reason why they extracted this number based on your prompt. And something that is also being done is reverse engineering. When you have what you have right now, a golden standard database of human coded, you then go back to them and say, what prompts would get me to the higher accuracy? And so not thinking what prompts you think should be in there, but asking LLMs or agents to improve the prompts so that you would get what the outcome of that is. And I think these two approaches right now that are used in medicine were very likely could be used in economic research.
That's very interesting. We definitely should look into this. And that's kind of like the response that we get from LLM experts, especially coming from public health and medicine, is that this can be done, and they're very confident it can be done. Some people have tried with these agentic approaches, and they get similar numbers in terms of accuracy. Perhaps the only thing I will highlight about this process is that we want to extract every single treatment effect in the paper. And that task, I think, is still a little bit difficult to do for LLM, not just the main impact, for example, that is described in the paper. But definitely, let's talk more. Thank you. Sorry. Oh.
Along similar lines, you can imagine, there's a bunch of LLMs that have got native PDF parsing right now, and others that are sort of other approaches that are coming online, like Andrew Ng also has a company now doing, PDF reading. I feel like one of the big trade-offs that you might be facing with trying to do things with the, very small models and deterministically, maybe this is earlier in the pipeline, but you can have potentially like a mixed approach of having the agentic, having a different approach for the extraction from PDFs in particular to JSON or whatever files versus having the categorization of all the extracted stuff into, so you can have a more mixed approach if you want to have like some parts still be the deterministic small model thing. I'm kind of in agreement with this guy from Stanford. Sorry, I forgot your name.
Sure thing. So, and for example, some of the professors that we are working at Northwestern, they are keen into doing this kind of stuff with agents. And I think we definitely should try it. As I said, I think it's more a personal thing that losing control about what being extracted, even if the agent give you some reasoning on what it was done, that reasoning and the decision that the agent made may vary for every single paper. And it also gets more expensive. And we just want to make it public. Thank you.